Hello, I am Dr. K.K. Misra from our classes. This is about queuing theory part 2. I have already completed part 1, the theoretical portion of queuing theory. I hope that you would have liked it, and for my new viewers I would say that this is a must watch video tutorial if you want to understand the queuing theory. Let me tell you that if you really understand it and you like it, please do not forget to subscribe my channel R classes. In this part 2 of queuing theory, I would just be covering the three topics, that is queuing structure, operating characteristics of queuing system, and deterministic model. Queuing structure. Normally, there are a number of possibilities or possible situations. Some of those are as follows, like first come, first served basis. When the order of service of customers is in the order of their arrival, the queue discipline is of the first come, first served type. Here we may have a number of examples that may be considered in our practical life. The people like a queue at the bus stop or railway station. The people who come first will board first the bus or even the railway station. Then we have last come first served basis. Sometimes the customers are serviced in an order reverse of the order in which they enter, so that the ones who join the last are served the first. Say for example, assume that letters to be typed or order forms to be processed accumulate in a pile, each new addition being put on the top of them. Thus, a just arriving task would be next to the to be serviced, provided that no fresh task arrives before it is picked up. Similarly, the people who join an elevator last are the first ones to leave it. Next, that is zero, service in random order. Herein, random order of service is defined as whenever a customer is chosen for service, the selection is made in a way that every customer in the queue is equally likely to be selected. The time of arrival of the customers is therefore of no consequence in such a case. The selection basically is made on, you know, the random order. We may have a number of examples for this also in our practical life. Then we have, say, priority service. The customers in a queue might be rendered service on a priority basis. The customers may be called according to some identifiable characteristics like length of job, for example, for service. Treatment of VIPs in preference to other patients in a hospital could be the better example for this. Now we will talk about simply the operating characteristics of queuing system. Rather, these are important terms which are used in solving the problems, different problems, and understanding the problems. And also the same may be termed as characteristics, say queue length. The average number of customers in the queue waiting to get service is known as queue length. Large queues may indicate poor server performance, while small queues may imply too much service capacity. That is the significance that this is why we talk of queue length. Then there is Another term, system length. The average number of customers in the system, those waiting to be and those being serviced. Large value of these statistics imply congestion and possible customer dissatisfaction of a potential need for a greater service capacity. Waiting time in the queue. The average time that a customer has to wait in the queue to get service. Long waiting times are directly related to customer dissatisfaction and potential loss of future revenues, while very small waiting times may indicate too much service capacity. Fourth, total time in the system. The average time that a customer spends in the system from entry in the queue to completion of service. Large value of this statistic are indicative of the need to make adjustment in the capacity. Then another term we use normally, server idle time, the relative frequency with which the service system is idle. Idle time is directly related to cost. However, reducing idle time may have adverse effects on the other characteristics as mentioned above. Now we will talk about the different queuing models, which are the main discussing points, learning ones to solve problems related to queuing theory. The queuing models can be categorized as being either deterministic or probabilistic. If each customer arrives at known intervals and the service time is known with certainty, the queuing model shall be deterministic in nature. The vast majority of queuing models are, however, based on the assumption that one or more elements of the queuing system can be expressed only in probabilistic terms. Hence, nearly all of the queuing models are of probabilistic type. Let us first talk about deterministic model. Now let us take a case here, a situation, and just try to understand that what happens actually at a service station when the length of, in fact, queue length starts increasing, when the service facility gets overburdened or overladen. In order to understand the whole concept, let us take a very interesting example here, wherein the customers arrive in the queuing system at a regular intervals and the service time for each customer is known and constant. This is why it is a deterministic model. Keep this in mind that we are talking about deterministic model. The first case where the customer arrive in the queuing system at regular intervals and the service time for each customer is known and constant. Suppose that customer come to bank's teller counter every 5 minutes. Thus the interval between the arrival of any two successive customer is exactly 5 minutes. Assume that banker also takes exactly 5 minutes to serve a customer. So the arrival and service rates are each equal to 12 customers per hour. In this situation, there shall never be a queue, believe me, and the banker shall always be busy with work. Another situation. Now suppose that a banker can serve 15 customers per hour. The consequence of this high service rate would be that the banker would be 4 by 5th of the time idle in the 1/5 of his time. He shall take 4 minutes to serve a customer and wait for 1 minute for the next customer to come. There would be, as before, no queue. So far as the two situations are concerned, there is no problem. If this remains the same, I mean, the situation will never be hectic. But if on the other hand, the banker can serve only 10 customers per hour, then the result would be that he would be always busy and the queue length will increase continuously without the passage of time, with the passage of time. It is easy to visualize that when the service rate is less than the arrival rate, again, please mind it, when the service rate, arrival rate and that the customers are coming at the rate at which the customers are coming per unit of time, and the service rate means the way they are being served per unit of time. So the service rate is when the rate is less than the arrival rate, the service facility cannot cope up with all the arrivals, and eventually the system leads to an explosive situation. Symbolically, let the arrival rate be lambda per lambda customers per unit of time, and the service rate is mu customers per unit of time. If lambda is greater than mu, that is the waiting line shall be formed, which will increase indefinitely, the service facility would always be busy and the service system will eventually fail. If lambda is less than or equal to mu, there will be no waiting time. The proportion of time service facility would be idle is just 1 minus lambda by mu. The ratio lambda by mu is also called, average utilization or traffic intensity or the clearing ratio. This is very important formula. This is represented by rho, a symbol. Here rho is equal to lambda by mu. Again, there are terms used for this. Say average utilization. In examinations, questions may be asked that calculate average utilization or the traffic intensity in the service system or the clearing ratio. So that is always lambda by mu. For the present model, if rho is greater than 1, the system would ultimately fail. But if rho is less than or equal to 1, the system works, and rho is the proportion of time it is busy. So this was all about the points which were promised to discuss in this video tutorial. For any query, you can write to ourclasses@gmail.com. As far as the rest topics are of this queuing theory is concerned, will be given in the next video tutorials. For more video tutorials on quantitative techniques and operations research, you can follow YouTube channel R Classes. Thank you. Please like, share and subscribe. Thank you very much. Have a nice time.